All right, welcome back. Let's go ahead and make some changes to our confidence interval. So our confidence interval so far has the formula that you take your sample mean and you're going to add and subtract the error bound, which right now is given by z sub alpha over 2 times sigma over square root of n. And we went ahead and did some examples where we assumed that standard deviation was known. This, however, for all intents and purposes, mainly for this class, we're going to almost never know the true standard deviation. And this is, again, the example that I have here written down is that it's true when there are no historical records for my random variable. Or a lot of the times you're interested in a variable because it changes. So most variables change over time. A good example of this could be, for example, rainfall or length of the rainy season, or maybe even the length of a storm. A lot of that changes over time, and also the variability tends to change. So unless we're fairly certain that there's a lot of historical precedent for the data that we're looking at, and we verified that the data seems to have the same amount of variability as before, we're not going to be able to say that we know what the population standard deviation is. So knowing the population standard deviation is going to be an unreasonable assumption. So we're going to ask, well, how can I continue to make a confidence interval if I don't know the population standard deviation? Because a lot of the time, that's what we're going to be dealing with. So it's very natural to go ahead and say, well, if you don't know the population standard deviation, why not replace it with S, the sample standard deviation? It's very natural, I think we can go ahead and say. Because we already know that my population mean, sigma, is well approximated by my sample mean, x bar. So is that also true for the standard deviation? And it turns out that the answer is no. So that's what I want to show you right now. By the central limit theorem, we can go ahead and we know that if you standardize, if you take a look at your statistic, your sample mean, minus the population mean divided by the standard deviation, so that's x bar minus mu over sigma over square root n, that's going to give you a standard normal distribution. Now the issue is going to be, well, what if you don't know sigma? If you replace sigma with s in this computation, do you still get a standard normal distribution? And it turns out that you don't. You're going to get a slightly different distribution. So notice that I'm doing the exact same thing here. I'm basically computing a z-score, how many standard deviations away are we? But I went ahead and replaced sigma with s. And so if I do that, it turns out I'm going to add more variability because the mean is going to be different from sample to sample, but so is the standard deviation. And so William Gossett, pictured here, is actually the person that is credited with discovering this. He worked at the Guinness Brewery, and so he needed help from a statistician to actually publish it, but he really gets all the credit for discovering this distribution. So let me go ahead and take sample after sample after sample. If I go ahead and simulate from a population that has a mean of 50 and a standard deviation of 10, let me go ahead and take samples of size 5 and just take sample after sample after sample. So what I'm going to go ahead and do is I'm going to go ahead and take sample mean, x bar, subtract the center, which in our case is 50, because I told you, and then I'm going to divide by the variability, which in the left-hand side is sigma divided by, and sigma is 10, remember, divided by the square root of my sample size, which is 5. And so if I look at that, this basically just says how many standard deviations is your sample from the true center of 50. You get the following distribution. And notice how normal this is. We don't really see a lot of data super far away. Maybe limited at 4. We did see one observation out here super far off to the left. But look at what happens if I do the same thing here. If I take the sample mean minus 50 divided by, instead of 10, I'm going to divide by the sample standard deviation, S. So in that sample size of 5, you also have to compute the standard deviation. And it should be close to 10, but not quite, because again, there's going to be more variability. So that's more or less the only change. And now take a look at your distribution. So it still looks very symmetric, but this time we have a lot more values that appear to be extreme values. So they appear over here. Notice that before my values more or less stopped here, but now I can see that these are more extreme values. So my extreme values occur more often. And again, that's due because of the fact that you're taking the sample standard deviation S. And sample standard deviation changes from sample to sample. So there's additional variability in here, which is responsible for these tails here. So we can see that for sample size 5, we have thicker tails. We are still pretty symmetric though. Let's see if anything changes if I go ahead and repeat this with samples of size 10 and samples of size 20. So again, I'm still looking at x bar minus center, which is 50, divided by s over the square root of n. So it's the quote unquote number of standard deviations. We already looked at this for size 5. If you look at this for size 10, you get the following distribution. And notice how this time we're still fairly limited to how close we are, but there's less of these more extreme observations. And then by the time, if you take samples of size 20, you can see that, hey, this looks very much the same as the Z distribution. Because remember, my Z distribution stopped right around here. You can see the Z distribution over here on the left. So we have the following observation. If you replace sigma with S, you're still going to get a symmetric curve, but you're going to end up with thicker tails. And that distribution that we're seeing here is known as the T distribution. And the T distribution has a slightly different shape for every sample size. So that's going to be our takeaway. When we work with the mean, we're going to have to work with the T distribution, assuming that we don't know the population standard deviation. It's going to be bell-shaped, but this time it just has thicker tails. And it's characterized by something called degrees of freedom, which is going to be your sample size minus 1. So here we observe what happens. Degree of freedom 1 is the red curve. Notice how thick the tails are and how it goes beyond 4 standard deviations to the left and to the right. 3 standard deviations, it looks like the blue, so slightly thicker tails. 10, sample size 10, that would mean degrees of freedom is 9. Notice how thin the tails become. And then sample size of 20, that means degrees of freedom is 19. And notice how much thinner the tails become until finally we make it to degrees of freedom of 30. And that's the blue curve that we observe on our paper. And notice how thin the tails actually are. By comparison, we have the dotted line, which is the normal distribution. So you can observe that the larger the sample size, the closer the shape is going to be to the normal distribution. So for all intents and purposes, when I sketch a T-distribution, I'm going to sketch a nice symmetric bell-looking curve, but with slightly thicker tails. And so let's just practice doing this. Find the T-value corresponding to the following scenario. We have degrees of freedom of 6 and the area to the right of 0.05. So you're dealing with T-distribution, so let's sketch a symmetric curve, thick tails, and we're going to jot down the degrees of freedom in the center. Degrees of freedom is 6, and I want the area to the right of some value that they're calling T has to be 0.05. And notice how familiar this picture looks. Because now what we're saying is we're going to use StatCrunch to find this value by writing out our probability statement that this is equivalent to saying this is the probability that your random variable, which in this case is T, lands to the right of this unknown value, and that probability has to be 0.05. So let's type this into StatCrunch. And so I'm going to go to Stats, Calculators. Anytime you have a picture like what we drew, you're going to go to Calculator, and you select the calculator that, basically the distribution that you're using. We are using a T distribution now. So select T, and notice how they're saying, what is the degrees of freedom? So we want to go back and type in degrees of freedom is 6. change this to the probability greater than. We delete the middle one, and the area to the right has to be 0.05. Select enter and note that you have the similar picture on your paper. So now we get 1.943. All right, let's go ahead and do this next problem together. And that'll be it for the t-distribution and critical values. So this is what we're going to go ahead and do. We're going to sketch, because it's a t-distribution. They're giving you a sample size of 15, which means that your degrees of freedom, remember, is the formula, n minus 1. So degrees of freedom in this case is 14. And this time they're phrasing it in the language of confidence intervals. They're saying, I want to be 95% confident. So it's still going to be the same idea. You're saying if you know how this distribution behaves, you know that most of the values that you observe are in the middle. So I'm saying that there's 95% of data points that are going to land in the middle like this. So therefore, I can go ahead and find alpha, which is the area in the tails. It's whatever's left. That's 5% to get to 100, which is the same as 0.05. So each tail is going to be half of that. Throw that into a calculator, and you're going to get it 0.025. So now I can go ahead and find what this number, by the way, this number here in the middle is 0. And remember that it was symmetric. So whatever you get for this number, which we're now going to call z sub alpha over 2. Oh, my bad, not z, but rather t, because this is a t distribution. Whatever you get on the right, it's going to be the same thing on the left. So this is minus t sub alpha over 2. So go ahead and find the missing critical value if your area to the right is 0.025. All right, thank you for joining me. Please make sure you watch this again if you have questions, and try out your homework. See you in the next video.